This video is to provide the solution to the final review questions. Okay, so I'm going to go over all the questions and provide the solutions and explain how each problem is solved. Okay, start with the first question. The first question is to compute the Laplace transform of a given function, typically in the time domain. So there are actually two ways we can compute Laplace transform of a given function. So one is use a definition. So the first one is we basically use a definition. Of course, I don't go to the very much detail about the integration part, but the definition of Laplace transform says the Laplace transform function is given by integration from 0 to infinity of the original function, okay, time e to the minus s times t and integrate over t, which end up having only a function of s. For this one, we can also split it into three different parts. Okay, so that's why we can integrate each one to get the integration. So this can be a little bit complex. The second approach is we can use the table, because a lot of functions, they are table to talk about how to map the function in the time domain to its Laplace transform. So by using linear properties, so we can do the Laplace transform. This one is just split by as three parts, which is Laplace transform 2t, Laplace transform 1, and Laplace transform e to the minus 2t. So Laplace transform 2t, you can also pull the 2 outside, and Laplace transform t, which is 1 over s squared. You times 2, you get 2 divided by s squared. Laplace transform 1 is 1 over s, Laplace transform e minus 2t is just 1 over s plus 2. Okay, so that's it. So the second question is about compute the inverse Laplace transform form. So the main approach we use to compute the inverse Laplace transform of a function in the S domain is to use the partial fraction expansion. So this example I give you is 2s plus 5 divided by s plus 2 times s plus 3. Okay, so the partial fraction expansion has three different cases, as we talked about in class. So first one is the real distinct poles. The second one is repeated poles. The third one is complex conjugate poles. So the key parts we distinguish these three different cases is by the poles, computing the poles. The poles is computed by find a solution when we set the denominator of the transform function to be 0, which means if we set the denominator to be 0 is s plus 2 times s plus 3 is 0. So we get two poles, which are s is negative 2, s is negative 3. So the real and distinct, because they are real poles and they're different, so they're called real distinct poles. If they have real distinct poles, the original function, the transfer function, the function can be written as, we can split them as a over s plus 2 b plus b over s plus 3, which actually we separate the two poles. If you can take this pole, it is negative 2, this pole negative 3. So you only have to figure out what is the a and the b value over here. So of course this is already computed over here. This is why I computed a and the b. Okay, I think I mentioned this one in the previous video. So a is given by the original function time whatever it appears over here. Okay, and then evaluate the value which makes this one be 0, which is s is negative 2. So do the calculation and you get a 1. And similarly, b is the original function time the denominator here, which is s plus 2. And you evaluate the value when s that makes this one be 0. Okay, so that which is s is negative 3. So by doing the calculation, we get that b is 1, which means the original function here can be written as 1 over s plus 2 plus 1 over s plus 3. Then we can apply the inverse Laplace transform. So generally speaking, we use a table to find the inverse Laplace transform. Okay, so we just have inverse Laplace is inverse of the two, the sum of the two, because they're equivalent. And then we use a linear property, which means we can, if it's the sum of the two, we can do individually and then compute the sum. Then we use a table to find the inverse Laplace transform, which is 1 over s plus 2, the inverse Laplace transform is e to the minus 2t. 1 over s plus 3 is e minus 3t. Okay, so this example does not include the other two cases I mentioned. One is repeated poles, one is complex conjugate poles. So you can check my previous videos if they are repeated poles or complex conjugate poles. The third question is about computing to compute the the solution to a differential equation using Laplace transform and inverse Laplace transform. Okay, so the equation gives you is x dot t plus 3 x dot t plus 2xt is 1. The initial conditions are given by x0, x dot 0, they all equal to 0. Okay, the first question to apply the Laplace transform to a bi-equation and compute the solution in the S domain. So general approach is we first compute the solution in the S domain, and then we do the inverse Laplace transform. So to find a solution in the S domain, we actually first to apply the Laplace transform and Laplace transform both for the equation, which means I apply Laplace transform both sides of the equation. Okay, here I drop the t variable, so to make it simple. And also I denote this big xs as Laplace transform xt. Okay, so once we have that, we actually, by using the linear property again for the Laplace transform, we can split those sums. Okay, as L of x double dot plus L of 3x dot plus L of 2x. So here L means Laplace transform, and right hand side is L of 1. Okay, so here we use a table basically. So the table talk about for x double dot, what is its Laplace transform? It's just s squared times sx minus s times x0 minus this one has to be this. Okay, s squared x0 s squared times xs minus s times x0 minus x0. So this is what is the x double dot Laplace transform? And this is for x dot is a 3 times sx0 minus x0 xx minus x0. Then 2x is, you can put 2 outside, it's 2 times xs. Laplace transform of 1 is just 1 over s. So here we use initial conditions to actually drop all those values, okay, because they're all 0. So once clean out a little bit, so we have s squared times xs plus 3s times xs plus 2xs, which is 1 over s. So here we don't have differential anymore, the derivative anymore. So we can put all the xs outside. So xs, we can consider those as coefficients. We put them together times xs, which is equal to 1 over s. So we can end up having the xs is 1 over s. We put this to the right hand side. So it's 1 over, but become divided by this part. So it is 1 over s times s squared plus 3s plus 2. So this is solution in the S domain. The second step is use a partial fraction expansion to find a solution in the time domain. Okay, exactly what I mentioned in the second question, but the case is a little bit more complicated. Okay, again, in order to find the inverse Laplace transform, I need to figure out which case does it fall under. Is a real distinct pose, or repeated pose, or complex conjugated pose. Okay, to do so, I need to compute the pose of the transfer function of the solution, the function, which is 1 over s times s squared plus 3s plus 2. To compute the pose, I set the denominator to be 0, which is s times s squared plus 3s plus 2 being 0, and which is equivalent to the case when s plus 1, and s plus 2. So here I just rewrite this part as the products over here. So I end up having 3 poles. S is 0, S is -1, S is -2. So fortunately, it's real distinct poles, so it makes our life easier. So we follow the previous in the second question. So because the real is distinct, so I can sort of separate them as A over S plus B over S plus 1 plus C over S plus 2. So I have to figure out the A, B, C values here. So the computation will be the same. A is the original function time the denominator over here, and evaluate as a value when the denominator is 0, which means the S is 0, because you set the whole thing to be 0, so the solution is S is 0. So you do the computation, you get a 1 over 1/2. So B, you do the same thing, the original function time whatever over here, you time over here, and then you evaluate the value which makes this one being 0, so be 0, because S is -1, which makes this be 0, so the S evaluate as equal to -1. So you do the whole computation, you get this -2, -1 here. Similarly, C, you can compute the value, so I won't repeat over here. So now we're plugging in the ABC values over here with 1/2, -1 and 1/2. So again, this is a simplified version. In other words, we can do the inverse Laplace transform of the original function is equivalent to the inverse of the 3 individually by using the linear property. So accordingly, if we use a table, again, we use a table to look at what are those functions associated with this function in the S domain. Okay, so I have the inverse Laplace transform 1/2 over S is 1/2. Inverse Laplace transform -1 divided by S plus 1 is -1 times E minus T. Inverse Laplace transform of 1/2 divided by S plus 2 is 1/2 times E minus 2T. Okay, so that's my solution. Okay, so this is a third question. Okay, so let's go to the fourth question. Okay, so fourth question is also a little bit more complicated. Is without talking about transfer function, it's about transfer function. So it's a little bit more complicated. So typically, for a given control system, we might have different blocks, or we use a block diagram to represent the closed loop system or the system. So here, before we can compute the solution, we actually have to compute the transfer function. Then we can apply to a different control input to get the outputs. Okay, so we have a few lectures talk about block diagrams, so I won't repeat it over here. So generally speaking, here is the block diagram. So we give input, output, and this is what the system looks like. The first question is to compute the transfer function of the about system. Okay, before we can compute a given input, compute output, we have to compute a transfer function. The transfer function for this is a unit negative feedback loop for the block. So I can use the property for this is unit negative feedback. So unit negative feedback is what happens over here is whatever we have over here divided by 1 plus whatever over here. Okay, so it is 3 over s plus 4 divided by 1 plus 3 over s times s plus 4. Okay, so that's my transfer function, which is ys divided by u sub s. To simplify a little bit, so I multiply both the numerator and denominator by s times s plus 4. So the numerator becomes 3, the denominator becomes s times s plus 4 plus 3. So I put them together, I get 3 divided by s to the square plus 4s plus 3. So that's my transfer function. So the next one is to compute the solution for the y sub t given certain input. So here I'm given the u sub s is 1, which is the impulse function. Okay, so notice that this is different from ut is 1. So if ut is 1, so u of s is just 1 over s. So here I give us is 1, which means it's an impulse function. So this one is a step function. So make sure you know the difference. Okay. So compute y sub t. So first one to compute y sub t, first compute the solution in the s domain. So y sub s, which is ys divided by u sub s times u sub s. So this is computing the previous step. It's just a transfer function. So the transfer function is 3 over s squared plus 4s plus 3 times the input. Input is 1, so I can just ignore it. So 3 divided by s squared plus 4s plus 3. Then I'm going to use the inverse Laplace transform to find the solution, which is L inverse of y sub s, which is L's inverse of this component. So I covered over here. So here I still use the partial fraction expansion to find the solution in the time domain. Okay, so again I have to compute the poles. The poles actually you set the denominator to be 0, which is s squared plus 4s plus 3 being 0. So s is -1 and s is -3. So they are real distinct. Real and distinct. So again I can use this guy can be written as, so this guy can be written as just the sum of these two, right? So I have to figure out just the a and the b value. So a is again the original function right over here, time what's denominator over here, so s plus 1. Evaluate whatever value that makes the denominator to be 0, so which means I have s -1. Okay, so the value is 3 over 2, and b follows the same procedure, is -3 over 2. Okay, so once I plug in those numbers in, so I get a y sub t is L inverse of the original one, okay, which is L inverse of the new one, okay, and I do linear property, so I can separate them. This one I use table to find the inverse Laplace transform. Alright, so last part is try to compute the final value of y sub t, which is limit of y sub t as t goes to infinity. So you just plug in those numbers we just calculated over here and compute this limit. Okay, so it's pretty straightforward because this e minus t will go to 0 as t go to infinity. E minus 3t also go to 0 as t go to infinity. So the sum of the two will be 0 eventually. Okay, question number 5 is about stability of a system described by a transfer function. Okay, so I'll give you 3 examples. So here to check the stability of a system, we use the Raoult's Hurwitz criterion. Okay, so which means we need to build a Russell array for each of these transfer function. So the Russell array is actually computed by this. So actually we have we put the horizontal line, the vertical line, and we put s to the whatever highest power we have from the denominator, which is s to the third, right? We reduce one by one order for each row. Okay, so s3, s2, s1, s0. So for the first two rows, we actually plug in all the numbers from the coefficient of different s to different powers. For example, here is 1s squared cubed plus 1s squared plus 1 times 0 times s, because I don't have it over here, plus 1. Okay, so coefficients is 1, 1, 0, 1. So I have 1, 1, 0, 1. So you fill the numbers by starting from the very top left, then you first row, then you go to the second row, still the first column, then you go to the second row, second column, first row, and the second column, second row. So you go so on and so forth. Okay, so I have 1, 1, 0, 1. If I have more, I have 1, 1, 0, 1, blah blah blah. You can keep on feeding these numbers. So this is how to fit the first two rows, and for the remaining rows, each entry is computed by I call it crossback rows. So this number, for example, this number here is computed by, you first look at the entry right above it. Okay, this is 1. You go cross in the product, is 1 times 0. Okay, back is minus. Then there's cross. This is 1 cross 1 times 1. Okay, then back. This means divide by the value 1 over here. Okay, so it's a crossback. So 1 times 0 minus 1 times 1 divided by 1. So it's negative 1 over here. Similarly, you can do the same rule, crossback. So this is 0. So 1 times 0 is 0, minus 0 times 0 is still 0, divided by 1 is 0 over here. So this guy do a crossback again. So this is negative 1 times 1 is negative 1, minus 1 times 0 is 0, divided by negative 1 is still 1 over here. So the Russell criterion has basically said that if the first column does not change sign, it's stable. If it changes sign, so it's unstable. So here, if you say it does change sign, because from 1 to negative 1, it changes sign. Also from negative 1 to 1, it's a change sign. So it is unstable. Okay. So follow the same procedure, we can look at the second example. So it's a little bit more complicated. So the highest part order from the denominator for the s is s to the 4th. So build the Russell array by starting from s to the 4th, s to the 3, s to the 2, s to the 1, s to the 0. So again, I figure out all the coefficients here is 1, 1, 3, 5, 2. So the 1, 1, 3, 5, 2. Of course, you put a 0. Always put a 0 if you want to have more. Okay. So you use the same principle I mentioned. So you do the crossback. So it's 1 times 3 is 3, minus 1 times 5 is 5, 3 minus 5 is negative 2, negative divide by 1 is negative 2. So you don't have to compute it any further because you already changed sign, so it's unstable. So this is one more example. So you follow the same procedure, okay, to build a Russell array. So s to the 4th, s to the 3, s to the square, s to the 1, s to the 0. You put in numbers, coefficients 1, 1, 1, 2, 5. So 1, 1, 1, 2, 5, 0, of course. When you compute the crossback, you have 1 times 1 is 1. My back is a minus, 1 times 2 is 2. So 1 minus 2 is negative 1. Back is negative, divided by 1 is negative 1. So it's still change sign, so it's unstable. Okay, so now let's take a look at the number 6. So one of the important application for the Russell criterion is we can also use the Russell criterion to check if the system is stable and also evaluate the range of unknown parameters such that the system is stable. Okay. So here is a consider control system with transfer function given by this g sub s 1 over k s to the 4th plus s to the 3 plus k s squared plus 2s plus 1. So our question is to determine the range of k if existing for the stability of the system. So it could be that we couldn't find any k, or if we can find any k, so what's the range of k? Okay. So the main principle we try to figure the range of k is also to use the Russell criterion. We still build a Russell array, which is the highest power here is s to the 4th. So I have s to the 4th, s to the 3, s to the 1, 2, s to the 1, s to the 0. Okay. So once we do that, we have k. We just put a parameter as a coefficient, of k1, k2, 1. So this is 1 because this is considered as 1 times s. Okay. So let me see. I still revise. So k1, k2, 1. Okay. So now you can compute all the numbers over here. You do crossback, cross back all the values of here, so I don't repeat it over here. So essentially what we coming up here is I have k1, I figure out all the numbers from the this row, and this row, right? First two rows are already filled in by the coefficients. So I start with third row, fourth row, last row. So the first column should not change. We know that according to Raskori criteria. So what we do is we don't make sure that the first column is k1, negative k, 2k plus 1 divided by k and 1. So that's my first column. So to make sure the system is stable, I make sure the first column does not change sign, which means because this is already positive over here, so this number should be positive. Otherwise, there will be a change of sign. So k must be positive first of all, and negative k also has to be positive, and also this 2k plus 1 divided by k has to be positive. So if you look at this one, these two got some conflicts, right? K has to be k positive, right? But also negative k has to be positive. This is not possible, right? So that's why the system is unstable for all k. So there's no k that can make the system stable. So this is question number 7. So question number 6. This is question number 7. So this question number 7 is about a root locus. Okay. So you can also view the previous video if you have a question about how to draw the root locus. This can be a little bit more complicated. Okay. So here I give you a system given by the block diagram. So here I have this is also unit negative feedback. So I have GCS block and the GS block. They are in a cascade, and then I have a unit negative feedback. So here G sub s is given by s plus 3 divided by s times s minus 1 times s minus 3. So we can also divide this as numerator and denominator. Apparent numerator is given by s plus 3, and denominator is given by s times s minus 1 times s minus 3. So the zeros and the poles, this is also called an open loop. Zeros and open loop poles. Okay, so they are determined. They are given by actually the G sub s. So the poles, zeros is when you compute a numerator, you set a numerator to be 0, and you compute a solution. So the open loop 0 is is negative 3, and the open loop pole when you set the denominator, which is D sub s being be 0, you get a poles are s is 0, s is negative 1, s is negative 3. So the first question is the one GCS is k. So how many lines are located in the plot of the root locus? So the root locus, the rules, one of 10 rules says the number of lines and number located determined by the degree of n sub s or degrees of d sub s, whichever is greater. So the degrees of ns degree is determined by the highest order of s. Okay, so here the highest order for the numerator is 1, right? S is s to the 1, so the degree of that one is 1. The degree of d of s is 3 because you do the multiplication, you get the highest power for s is s to the cube, right? S to the 3, so this is 3. Degree is 3. So the highest one of these two is 3, right? Because this 3 is greater. So I have 3 lines and 3 loci. A follow-up question for the first for A is what are the starting and ending locations of the line? So the the root locus, one of the rules says that the lines and lines always start with an open loop poles and ending at an open loop poles, which means I have open loop poles already calculated over here, which are s is 0, s is 1, s is 3. So your starting position is just 0, 1, and 3. The ending location is the open loop zeros, which is s negative 3. Unfortunately, I should also have 3 ending location, because I have 3 starting location. I must have 3 ending location, right? So one of the rules says if they are not enough poles and zeros, those lines will go to or come from infinity, which means this guy starting from this guy 0, 1, 3, ending at a negative 3, but there must another 2 endings, right? Because I don't have those endings, so this will, according to this rule, it will go to infinity. So 2 of these lines will go to infinity. It's not coming from, because the ending is infinity, so it's go to infinity. Okay. So this is part A. Part B said when GCS is k, we want to sketch the root locus. Okay, we actually want to draw how the root will change. So essentially, what it says is, what if I want to move this k? Let's say I have k over here. Okay, I want to change the k from 0 to infinity. I want to see how the closed loop system, the pole, the closed loop will change when I move the k from 0 to infinity. Okay, so this is what the root locus is about. All right, so let's that's the first part, typically the procedure. Okay, you can also view my previous video if you have a question about how to draw the row locus. Okay, the first one you want to find, you draw the horizontal line and vertical line, and with the real and the real axis and imaginary axis. Then you draw the zero in the pose. Okay, so for the pose you use x, cross x to represent the pose. So I draw the pose up here, 0, 1, and 3. Okay. Also I draw 0. 0 I use circle to represent that is actually -3. -3, yes. So then I have the probably saying that order the zero pose. Okay, the zero pose are ordered from the right to left. Okay, so the 1, 2, 3, 4. Okay, this is 1, 2, 3, 4. One of the rules says to the left of the odd number of zero pose on the real axis parallel-key. Okay, what this says is this odd number is number 1 odd to the left of it. Okay, on the real axis parallel-key. You should stop over here because otherwise this is to the even number of left of the even number, so it wouldn't apply. So this is parallel-key. Okay, so this is also parallel-key. Okay, this is to the odd number, number 3, right? This odd number to the left of it, this is parallel-key. Okay, so now you can sort of see this because the line must start with the pose ending the 0, right? So start with here, pose and ending at 0. So you can sort of see one line like that. It's starting from here and ending over here. Okay. The next one is, how about this two? These two will go to infinity because, as I mentioned before, they don't have enough zeros, so they will go to infinity. You have to check how it will approach infinity. We actually have to compute what is the asymptotes. The asymptotes is determined by the angles and also the centroid. So the angle is computed by phi a, which is 2q plus 1 divided by n minus m times 180. That's the pose of the angle of the asymptotes. So okay, so and the angle, the number of angles determined by q, which is starting from 0 to until n minus m n minus 1. So n here is degree of d of s. We already computed before, is 3. M is degree of ns, which is 1. Already computed before. So q should start from 0 until n minus m and minus 1. N minus m minus 1 is 1. So I actually have two values, q is 0 and 1. So apparently that's reasonable because I have two poles that will, the two lines that will go to infinity. So I need to have two angles basically. So to compute the angles, you just replace q by 0 and q by 1, calculate two values over here. So I don't want to repeat over here. So one of the angles is 90, one of the angles is 270 degrees. So one is going up and one is going down. So the centroid is determined by the summation of poles minus summation of zeros divided by n minus m. So poles are 0, 1, and 3, 0, 1, and 3, and the zeros are only -3. So you do 1 plus 1, 0 plus 1 plus 3 minus the pole, 0 is -3 divided by 2, so it's 7 divided by 2. So actually the asymptotes are actually given by centroid at 7 over 2, and one going up, one going down. So which means the lines will gradually approach these two lines, the two asymptotes, right? So sort of can see roughly gonna have to split, otherwise it wouldn't approach up and down, right? So it sort of split at a certain point, and one will approach, then going up, gradually approach the asymptotes. One's going down and approach the asymptotes. That's what it looks like, roughly. Okay. So apparently here, the problem over here is the system wouldn't be stable for any k because it doesn't matter the poles. These two poles are always on the right hand side. Okay, because you can sort of see they're always on the right side. Although one of them is on the left, in the left half plane, but this one is always on the right half plane. So this is not stable for any k. Okay, to make it stable, we have to sort of change the control, which means if you only have a GCS as a k, it wouldn't work, right? So one idea we make it work is that we want to change the GCS component here as k times s plus 2. Okay, so we want to see, hey, does this work? Okay, would that be able to stabilize the system? And also, what is range of k to make it stable? Okay. All right, so now we plug in the GCS by k times s plus 2. So the difference here is originally I have here is only k. Now I change this one to k times s plus 2. Okay, so now I want to go back over here. So I plug it in, so I sort of rewrite the system as this. Okay, remember in order to use the 10 rules I mentioned in class for the plot of row locus, I need to write in the sort of standard form. The standard form said I only have k over here, so other part should go back to over here. I only have k over here, other part should be known, no k over there, and also should be as absorbed in the new g sub s. So I sort of can move this s plus 2 to this one. It doesn't affect my transfer function at all. So once we do that, we sort of have the standard form. Now for this new g sub s, I have to compute this. So I sort of reassign the g sub s, n sub s, and d sub s over here. Okay. Now here's I have computed it. Of course, I need to compute the open loop 0 pose. Open loop pose, actually you set the d sub s to be 0. Okay, so this is again, you set to be 0. So s minus 1, and s minus 3. You set to be 0. So which should give us the 3 pose. S is 0, s is 1, s 3. And the 0 open loop zeros, you do the same thing. You sort of do the same thing. Okay, you set s plus 2 times s plus 3 is 0. So you have 2 zeros, which is s negative 2 and s negative 3. Okay, so follow the same principle. So I'm going to draw a real axis and imaginary axis. I'm going to draw also 0, 0 and pose. The pose it would be the same, still 3 pose over here. So 0 is actually one of them is negative 1, one is negative 2. One is negative 2, one is negative 3. So I draw the zeros over here. Okay. Now I'm going to label the sequence. So starting this is from right to left. So it's 1, 2, 3, 4, 5. So according to the rules says that to the odd left of an odd number of the zero pose of the real axis is parallel, which means this is a parallel. This is to the left of the odd number 1. This is also parallel between 3 and 4. So this is also odd number. Also all the way to infinity will be parallel. Okay. That's one of it. And also somehow over here you can sort of see this wall from the pole to 0. Yeah, this sounds good. So this is a one line. So this one we sort of see. So this guy, this 2, right, starting from 0 pose and it must go to 0, right? You sort of can see this must split. It should go somewhere, then go 1 over 0, right? Of course, the other one will sort of go to infinity. This is what's happening. Okay, so I must split at a certain point and start then, because also they must be symmetric. One of the rules says they must be symmetric. Okay, so they must go and start to merge here, then go to 0. Otherwise, this wouldn't be starting from pole ending at 0. Okay, we sort of see it's starting from those numbers and ending at this. Okay, let's put over here. Starting is 0, 1, 3. That's a pose, and ending at negative 2, negative 3, and infinity, right? So it must ending at this point. So you must split and also must join the real axis, then merge to this line. Okay, right? Okay, so then we want to figure out, hey, what is the centroid? Also, we can find once you go to infinity, right? We want to figure out what is the asymptotes, which means the angles and the centroid. Okay, so because it's only one line, so actually you only have one angle and one centroid, right? The angle is phi a, which is 2q plus 1 divided by m minus m times 180. So here the q has to start from 0 and 1 until n minus m minus 1. So here the difference here is n here is 3, m is 2, right? So n minus m minus 1, n minus m minus 1 becomes 0. So which means I q can only select 0. Okay, that's why I only have q 0 here. So I just plug in q 0. I have phi angle is 2 times 0 plus 1 divided by 3 minus 2 times 180. So this gives me 180 degrees. The centroid is computed by the sum of the poles minus sum of 0 divided by n minus m, which is 0 plus 1 plus 3. Actually, we have 2 zeros. One is negative 2, one is negative 3. We do the sum of the 2. So it's 4 minus negative 5, which is 4 plus 5, which is 9. 9 divided by 3 minus 2, which is 9. So you sort of can see, I'm going to have the centroid is here, and angle is 180 degrees, going to all the way left. This is, you're going to approach this line, right? Which is actually match what we're drawing over here, because it's going to split. Okay, and then one of them going to this zeros, and one of them follow this asymptotes, do not go to infinity, negative infinity. So the 3 lines that can be drawn over here. One is starting from this line goes to zeros. Okay, Then this one is one line go here, and they have to split. One go up and go here. The last one to go here and going down and to the left. So that's the 3 lines. Okay. So apparently, as you can see, it's sort of here. So this guy will, as k increases, it's going to move to this 0. So it's great, which means it's going to the left half plane. And also it's good for this too, because they have to split and gradually move to the left half plane. And one go to this -3, one go to -infinity. So there's a critical k value called k star over here. Once it's past this value, greater than this value, it's going to move to this left hand half plane. Okay, so we can see sort of this will be stable for some big k. Okay, so to determine the range of k such that the system is stable, so we have to compute the closed loop transfer function with also the unknown parameter k over here, right? So we sort of can see this is the transfer function y sub over u sub s given this one, okay, given this one, okay, given this form. So it is k times g sub s, okay, divided by 1 plus k times g sub. Remember here, g sub s is a new one. This is a new one I use over here. This is a new form, okay. Now do not use the previous one, okay. So this one I plug into the new g sub s, is s plus 2 divided by s plus times s plus 3 divided by s times s minus 1 times s minus 3. So if I multiply both the numerator and denominator by the s times s minus 1 times s minus 3, so I'm ending up cancel out the denominator over here like this. This will be cancelled out, and also this will cancel out. Of course, you have 1 over here, so you have to k times s plus 1 times s plus divided by s times s minus 1 times s minus 3 plus k. This will be cancelled out, so k times s plus 2 times s plus 3. So if I clean up a little bit, okay, the numerator I don't have to care about it because it has nothing to do with stability. So denominator I clean a little bit, so I get this one, s to the cube plus k minus 4 times s squared plus 3 plus 5ks plus 6k. So that's the new form of my denominator. Now I can use the Ras-Horowitz criterion to check the range of k such that the system is stable. Okay, this is follow exactly what I mentioned over the question number 6. Okay, question number 6. Okay, let's go back to this form. So I draw the Ras-Horowitz to build the Ras-Horowitz. So I'm using a vertical line, horizontal line. So the highest order is s to the 3, I start with s to the 3, s to the 2, s to the 1, s to the 0. So the coefficient are, I can see this is coefficient of 1 times that. 1 times s goes to 1. The second one is k minus 4. Third one is 3 plus 5k. And last one is 6k. I can multiply 0 over here. So I use again the rule called cross back to find all those the second row and the third row and the last row. So this one is given by, for example, this starter is given by this cross, which means this guy times this guy. Back is minus 1 times 6k, right? This is 6k. So 1 times 6k is still 6k. And back is divided by k minus 4. So this delta is given by this form. And this guy is 0. You follow the same rule. This is 6k. You follow the same procedure, cross back. Okay. So according to the Ras-Horowitz criterion, so the first column of my mass array should not change sign, which means this one, because this is already positive, so which means the other ones, they must be positive, otherwise they will be change of sign. So which positive means k minus 4 has to be positive, okay, delta has to be positive, and the 6k has to be positive. And this k minus 4 positive means k has to be greater than 4. So automatically this will be positive, because if k greater than 4, so 6k greater than 4, so 24, so it should be greater than 0. So this one I can just ignore this. This one can be ignored, okay? So I have to figure out, hey, under what condition that this guy is positive? Okay, because here k is greater than 4 already, so I can also ignore this denominator because this is positive, right? So which means this is, you couldn't say I have to figure out what is the numerator this guy is a positive, which means this guy is a positive, okay? So if I simplify a little bit, so I try to calculate all the product out, so I have 5k squared minus 23k minus 12 has to be positive. So this side, I'm drawing how it looks like roughly for different k, how this guy will change, okay? Sort of like that, okay? Because k is very positive, k squared really big, so make it a positive. When k is really big, I also make it a positive. When k is somehow in the middle, so it can be negative. So it's sort of there's a critical value of this k star. Once it greater than k star, it's going to be positive, right? So again, I want it positive. So eventually you want a k star to be the value. So this k star is given by the value when you make this one to be 0, which means essentially 5k star squared minus 23k star minus 12. This guy has to be 0. This is a value. As long as you're greater than that value, critical value, then that's great. So this critical value k is greater than what? It's using k should be greater than 23 plus square root of 23 squared minus 4 times 5 divided times 12. This is actually given by, if I do this one, is a times k squared plus b times k plus c equal to 0 for this one. So the value that makes this quadratic form to be 0 is k is 2a is negative b plus or minus square root b squared minus 4 times a times c, okay? Because here I must have k to be positive, so actually this is just this. K is 2 negative b plus divided square root plus b squared plus 4ac divided to a. So that's why how I get this value over here, okay? So which means I get this a, you consider a is 5, okay, a is 5, so it's 2 times 5, this b is negative 23, so it's positive 23 plus square root of negative 23 squared is same as 23 squared minus 4 times 5 times negative 12. Okay, so let's make this negative 23 squared. Make it be straightforward. Okay, that's 2 times. So this one becomes 23 plus 23 squared plus 240 divided by 10. So which means if my k is greater than 23 plus square root of 23 squared plus 240 and divide by 10, then my value will become, this is also this value. This is exactly what this value is. You can write down over here. So this is 23 plus square root of 23 squared plus 240 divided by 10. So that's the k star value. As long as k is greater than that, the system is stable. So this is all about the review, the final review, all the solution to the final review.